So when we spoke about ProVerif, at the end I showed you how we analyzed TLS 1.3 in ProVerif. And I kind of showed you, in a way, what's the best feature of ProVerif for that particular kind of analysis, which is that you can analyze the protocol for things, for logical flaws, by which I mean things like downgrade attacks, synchronization attacks, and these kinds of things. So where you can mess with the protocol just by changing and changing messages and things like that. So once we have verified that TLS 1.3 does not have a certain kind of, at least our model of TLS 1.3 is safe from downgrades. Now we want to take the core of the protocol, which is TLS 1.3 itself, and forget about TLS 1.2 for now, and try to prove that it satisfies some security goals. And there are many papers already which have done proofs of various draft versions of TLS 1.3, and I think Mark described at least one such work a couple of days ago. Perhaps Hugo described something on Sunday, but I wasn't here. But various versions of TLS 1.3 have already been proofs of. So our idea was, well, let's try to mechanize the proof in CryptoVerif as a way of first checking that the proof works in a machine-checked way, but also of exploring the limits of what our tool itself can do. And so it's a case study in two ways. We're going to show how we can analyze TLS 1.3, very briefly, really. And but more than that, we're going to see all the assumptions that we need in order for the proof to go through in our model, which may not have been necessary in the other proofs, because our model may have some certain syntactic restrictions that we have to obey. In particular, because we're using a tool which is extremely syntactic on how it deals with game transformations, we are not able to do some of the intuitive leaps that you might be doing in hand proofs. All right, so what did we do? We took the TLS 1.3, this was for draft 18. We updated the proof a little bit, but not so much, and coded it up in CryptoVerif. And what version, what parts of it did we prove? Did we code? The handshake with pre-shared keys and/or Diffie-Hellman, the handshake with and without client authentication, the 0 RTT data, which means data that is sent along with immediately after the client hello, and the 0.5 RTT data, which is something that is kind of weird about TLS 1.3, where when the client sends you a message to a server, the server can send back a response and immediately can send back some data before the client has responded. So this is what we call 0.5 RTT, which is like the data that is coming back from the server before the client has confirmed the session, before the client has sent its finished message. So we included that, and the idea of key updates, which means after the session is completed, you can still update the key by hashing forward effectively. However, we did not cover things like post-handshake authentication. We threw away all the cipher suit negotiation like we do in crypto proofs because it's just too complicated to deal with. We do not really consider the compromise of pre-shared keys, but we do consider the compromise of certificate private keys for forward secrecy. Okay, so what we did was to prove individual. Okay, so the proof structure was roughly like this. We actually proved 3 different scripts correct. The first script was the handshake without the pre-shared key. And then once the pre-shared key is established, there's a handshake with the pre-shared key which can refresh the pre-shared key. And then there is the record protocol which uses the key material which is provided by either of these 2 boxes. The fact that these 3 boxes can be composed together and give security guarantees for the whole protocol was done by hand. It wasn't done in CryptoVerif. CryptoVerif was used to prove each of these 3 individual boxes secure with respect to a specific definition of what we are trying to prove. In particular, okay, so what did we need in order to prove the properties? And in some ways, this is probably the most, in almost all CryptoVerif proofs, I would say, the most interesting part of the proof is at the end of it, you basically have to list all the assumptions you had to make to push the proof through. And then you can look through these and you can say, well, is that a reasonable assumption or not a reasonable assumption? And I'll leave it up to interpretation. So for Diffie-Hellman, we used the gap Diffie-Hellman assumption here. We could not really make it work with the PRF or DH assumption, specifically for the 0.5 RTT data, which you wanted to cover. But it may also be a limitation of CryptoVerif that we were not able to find the right variant of PRF or DH to make it work. It's kind of an open problem. We are still thinking about it. But we use cap Diffie-Hellman for the Diffie-Hellman assumption, which is a standard assumption which is already in the CryptoVerif library. Then we made a bunch of slightly weirder, sort of more unusual assumptions. Well, okay, the Diffie-Hellman group has to be of prime order, whatever. The Diffie-Hellman group elements all should be different from 0, okay? And this was an assumption we needed in order to disambiguate the case where in some modes you use a Diffie-Hellman key, and the pure PSK mode you do not use a Diffie-Hellman shared secret, and in that mode you use zeros instead. So in order to disambiguate these two cases for the tool had to syntactically distinguish between these two cases. We made this assumption that all Diffie-Hellman group elements are going to be different from 0. And this is true as long as you are doing public key validation, that is going to be true. So it's not a super unusual assumption. The other slightly more unusual assumption is that we assume that all Diffie-Hellman group elements do not have this format. And this format is that it should not be of the form where there is the length of the hash function concatenated with the string TLS13 concatenated with two things ending with 0x01. And although it looks super ugly and weird, why should I make this particular weird assumption? It's because in the key schedule there's a particular place where there's a collision or potential collision. Right? The point is that the formats of the two elements in the key schedule look the same to the tool. Syntactically they look the same, and they cannot be disambiguated. And they are basically the HKDF extract of ES and E and the derived secret applied to ES and PBK and blah blah. And if you look at those three values over there and you expand their definitions, you find that you have these values which you have to disambiguate. And a priori, you may not be able to disambiguate them. Under certain assumptions, it might be obvious that they are not going to be the same. But if you make this assumption, you can cleanly disambiguate between them. Interestingly, as we were doing this proof, there was a discussion on the TLS mailing list where a similar kind of problem was brought up about, oh, how do we know that this particular place in the key schedule is not going to be the same value as generated in this other particular place? And even though it was probably very unlikely that those two values would collide, they decided to add an extra HKDF extract or derived secret stage before an HKDF extract to basically resolve this ambiguity in a different way. They didn't have to make this ugly assumption. Instead, they just said, okay, let's change the key schedule so that this problem will not occur again. And indeed, we verified that after you make that draft 19 change, we don't need this assumption anymore. We can throw it away. Yeah, I mean. Well, I'm not sure actually it's an attack because it's an intermediate key in the key schedule. So what it. Right. Indeed. So I mean. Yeah, thank you. So yes, indeed, that is the case, that if this were a different protocol and you had a similar assumption, it might well be the case that if the attacker had full control over choosing that particular element, it was like a public key that the attacker sent you, and he chose something of exactly that format, he might be able to break the protocol. In this particular case, it's an intermediate value, which is very unlikely to have that format. But if it did, then you cannot apply the cryptographic assumption you need in order to get to the next stage. So we needed that in order to apply an assumption at a particular place. So it's kind of a technical condition, but indeed it is an ambiguity that appeared in the key schedule, which was then resolved in TLS13. What other assumptions do we have? Signatures, UFCMA, standard. Hash functions, we assume are collision resistant. We need that, in fact. So all the hash functions in TLS13 have to be collision resistant in our model. For HMAC, we use, well, the standard HMAC assumption, but also a couple of that the fact that the HMAC, when used with 0 as the key, and HMAC when used with KDF 0 as the key, which is the KDF applied to 0, are independent random oracles. And we needed this assumption in order to disambiguate against, again, two cases that occur in the key schedule. And other than that, we need the HMAC function for the whatever hash function we use to be a PRF for keys that are not those two keys. Okay, so if you're using 0 and KDF0, you need them to be independent random oracles. For all other keys, we need it to be a PRF. So those two are special case of the HMAC that is used very early in the key schedule. And after that, you use HMAC in a very standard way. So we have different assumptions for different places in the key schedule where you're using them. And we need them in order to apply our assumptions. Okay, so and for the authenticated encryption algorithm, we use pretty reasonably standard assumptions that it's in CPA and in CTXT, and assuming that the same nonce is never used twice with the same key. And in fact, in TLS13, we can show that in fact the same nonce will never be used with this twice with the same key, and so that's as strong as we need it. Yeah.
Sorry to bring you back. You said that the three things that didn't work are these because they're inherently difficult, or you just need more quickly?
You mean those minus ones?
Yeah.
No. Well, this one is, I think, not particularly more difficult. It is just that it's another stage that you have to add to the protocol. We did 3 stages, and we didn't do the one more stage. This one is negotiation. This would be, so negotiation only makes sense to verify if you're going to actually add some weak algorithms as well. And that, if you added some weak algorithms to the, negotiation with only strong things, we could have added, no problem. Negotiation with strong and weak things, maybe with TLS1, 2 as well, that would have expanded the model so much that our proofs would have become much harder, because our model here is already big enough that we had to provide a lot of user help for the prover to prove it. It would have become far larger. Maybe not, but we tried a few extensions and we kind of got scared and we stopped. Okay. This one again is we just didn't do it, but we could do it. I don't think that's a big deal. Okay. So with those assumptions, we are able to prove the standard kinds of properties: secrecy, forward secrecy, authentication for the keys generated by the first 2 stages, and for the messages sent and received by the record protocol. The details are in the paper. I'm not going to get to it, but the informal theorem basically is that our system that we are proving things about contains is about the key. Is initially about the key exchange, and A and B we obtain a key for which we have the key secrecy, which means the keys obtained by A are indistinguishable from independent random values. One-way injective authentication, which means that for each session of B where you obtain a key K, there is a distinct session of A that obtains the same key K, okay, with the same transcript. So the transcripts are the same, and for every key that I establish, there is a unique peer session which has the same key. This is at least true for the main session key. For 0 RTT, it's actually not true on the server side because of the replay problem. Then there is the same key thing, which is that if the transcripts on A and B are the same, they will actually derive the same key. Okay, so those are the sort of the 3 properties that we proved. And then we informally define a new system S prime that assumes that the key shared by A prime and B prime is fresh, and then show that you can actually compose this in 2 or 3 steps. So you can actually run the first handshake, then you can compose it with the resumption handshake, assuming that the keys are fresh. You can compose that with a record protocol, and you can actually run the resumption handshake or a PSK handshake any number of times as well. So that proof, which is the composition of all of these things, is actually done by hand. Okay? Okay, so conclusion of mechanized proof of TLS13 is we are able to prove all those things, but not the other things. And we do some proofs by manual composition. We needed to break the protocol down into these boxes. So not just for the beauty of the proof, but because the tool was actually not able to handle them all together. So if you did them all together, the size of the games, because every time you apply a game transformation, the game could double in size, let's say. It could actually double in size every time you do it, because there are 2 different cases that might get disambiguated. You double the size of the game. So if you have 20 transformations, you're like getting much bigger, right? So the larger the protocol, and it's not really about lines of code, it's about the depth of the number of dependent transformations that you have to do. And since TLS13 has a sequence, it's a key schedule with a sequence of things, each of which is dependent on the previous one, the size of the games actually can become huge by the time we apply all of these syntactic transformations. When you're doing manual proofs, you can keep contracting back the game because you realize what's happening and you're like, okay, this is similar to something else and I can keep contracting it back. But when you're doing it for the tool, it just gets bigger and bigger because it's actually disambiguating syntactically all the various cases. And so it became quite difficult for us to handle. So we're trying to improve the tool which can actually, so that it can handle these much larger proofs more gracefully. But for now, what we do is we kind of prove individual modes and we prove that they can be composed by hand. Several hundred, for sure, in each of those cases. Most of them are syntactic transformations, simplifications, let's say, because the number of actual crypto games you have to apply is, I don't know, 16 messages, right, or something, I don't know. So maybe there are 16 or 20 real crypto games to apply. Most of them are PRF games, but yeah. Yeah, so every time you apply a game, the formula gets bigger and bigger. Every assumption, yeah. So Cryptoverif is able to, well, to evaluate such formulas, let's say, for under certain assumptions, and so tell you that this is negligible, so you end up not looking at the formula at all. But if you actually looked at the formula, it's yes, and non-negligible utility. So negligible utility, let's say, yes. All right, so that concludes my part on Cryptoverif, and I'm happy to kind of help you guys install the tool and run things later on if you want to show you more examples. I'm going to put up the scripts that I used here for both Proverif and Cryptoverif on the course website as soon as I'm done today speaking, which is going to be, I think, in a couple of hours after the next break. But essentially, I'm hoping that you guys will try it out at least, because it is a prover that is capable of doing fairly standard steps of fairly standard crypto proofs. But it usually struggles when you're going into really fancy crypto. So we would love to learn where the limits are and expand them for you if need be. This is a summary. The security assumptions you have to define, or you can use standard assumptions, or if they're not standard, you can define them as observational equivalences. The protocol is defined in a syntax which is called a process calculus, much similar to that of Proverif, but each process you can think of as an oracle, really. It's not so different in the way you write it. And the prover is basically going to produce a sequence of games for you and a probability of the attack. Okay? The user can provide proof scripts and interact even interactively, which is to say, you can ask for the current game, you can look at the game and you can say, oh, try this transformation, it'll give you a new game. So you can actually interact with the prover to actually discover the proof, if you like, and that kind of works reasonably well for a certain size of program, for a protocol. And it does do Diffie-Hellman and so on, but you can also, we also want to add other primitives for including the full support of XOR, which is not fully supported yet, and more transformations, more case studies, and so on. So we've used Cryptoverif to do a reasonably complete proof of signal and of TLS13. So we think it's ready for modern protocols, but we haven't done a number of other things which you guys might be interested in. So I'm looking forward to kind of discussing what you might want to prove in it. That's a good example, yeah. Mm-hmm. Okay, we'll take that challenge, yeah? Could you speak a little bit louder? No, I would say. So this is a forward proof tool in some sense. It is, you can use the tool in certain ways to kind of try to explore the possibilities of what you might need, but it's not very good for automatically discovering what you might need. So you have to, in other words, Cryptoverif proofs work best if you already have a proof sketch on paper and you want to just make sure that every single step is dotted and crossed, and And that's what the tool is good for doing. It's not really good for discovering new proofs. The proofs that it will give you, even if it gives you automatically, are pretty much brain-dead ones that you would have done yourself. Plus, just making sure that all the corner cases are handled right, and you've not forgotten some mini lemma you needed somewhere. So it's mainly for machine checking your intuitive proof that you would have written by on paper. Okay. Let's now move to the last part of what I wanted to speak about. I don't know how much time is left in this session.
20 more minutes.
Okay, so we're going to do this for 20 minutes, and then we're going to have to empty this room out, and then we'll continue after the break elsewhere. Okay, so we saw how to find logical flaws. We saw how to do some crypto proofs. Of course, there's a lot more we could talk about there. But now let's move on to implementations, right? So when I say cryptographic software, I'm basically saying any application out there which is using crypto and in a program. And there's a shocking number of web applications, for example, which are now using crypto, and they're using usually ad hoc crypto protocols, and they're implementing themselves and so on. But even otherwise, even if you forget about the ad hoc so-called military-grade encryption, which is used by web applications with usually all kinds of bad terminology, there is still at least a few that we are all concerned about, like protocols, like implementations of TLS, SSH, Signal, OpenID, and so on, and certain kinds of end-to-end encryption systems like cloud storage that we all use. So the observation is that coding with crypto, or coding crypto and coding with crypto, are both quite easy to get wrong, even for experts. There's a ton of bugs, a ton of attacks that come up all the time in implementations. So how about we use formal methods to also improve the assurance in the implementation of our crypto protocol, of our crypto construction, not just in the design. So that's what we're going to focus about in this last part. In particular, I'm going to observe that in TLS, one large selection of what goes wrong is in fact implementation bugs like heartbleed, state machine attacks, and so on. And we want to be able to prevent those kinds of attacks. So let me kind of summarize the kind of attacks that recently have been found in TLS libraries and in various other places as well. So the first class, which is of attacks, which is sort of the lowest sort of layer of attacks, is bugs in crypto primitives. So we will see some of them in the talk to come. So you can your crypto algorithm itself may actually produce incorrect results or may have side channels, and you might want to prevent that because otherwise your keys might be at danger. Another class which is probably even more popular or widespread is bugs in crypto usage. So the crypto primitive itself is fine, but it requires some preconditions on how it's used correctly. And if you use it incorrectly by reusing nonces, for example, then things go bad. We already saw bugs in protocol state machines. And there are tons of bugs in packet parsing, certificate parsing, and these kinds of things, which are boring parts of the code from a crypto viewpoint, but in fact often are the bigger kinds of bugs that people find in these kinds of applications. But for the most part, let's ignore that. So in this part of the last part of my lectures, I'll be talking about how you can extend the verification guarantees of your protocol all the way down to implementations. In particular, we look at how to build a verified crypto library and then extend it up to a verified protocol library. And the crypto library I'll be talking about is called HACL, and the verified library is called MeTLS. Okay? I won't go into too much detail. I just want to give you some ideas. I want to show you some code, this kind of stuff. There's a bunch of reading material. You can go look at them. All right, so let's start with crypto library for the next 15 minutes. We'll continue after the break. So suppose you wanted to build a crypto library for TLS, because all TLS libraries obviously require a certain set of crypto primitives, right? In particular, they need hash functions. They need SHA-2 for sure. Hopefully they don't need SHA-1 or MD5, but they probably do right now. They need Diffie-Hellman, so for which typically right now you would use P256, the NIST curve, or this curve called curve 25519, which is becoming more and more popular. You might also do mod P Diffie-Hellman using at least, say, hopefully 2048-bit groups. Hopefully you're not using DH512 anymore. You need signatures, and for TLS 1.3 you need RSA PSS. For TLS 1.2 you need RSA PKCS1 v1.5 signatures. You may also need ECDSA signatures for your NIST curves if you want, or EDDSA signatures if you're willing to go all the way to ED25519. And for the record protocol, for the actual authenticated encryption, you need some kind of key derivation, and TLS 1.3 typically relies on HKDF, and TLS 1.2 uses some version of HMAC for key derivation. And you need some AAD schemes, right? You need at least a ESGCM, you need CHA-20, Poly 1305. So these are the minimal set, the ones in black are the minimal set of things that your TLS library is going to need, right? And obviously if there's a bug in your implementation or an attack on any of these primitives, you're likely to be, to affect your protocol implementation immediately. So this is the core, the heart of any crypto protocol, any crypto software is going to be the crypto library. So it's the first place where we should make sure that all the screws are tightened and everything is perfect, because without this we are not going to be able to build up to a verified software stack. Okay. For the most of this, I'm going to focus on some of these primitives like curve25519 and poly 1305, but the argument is kind of similar. So let's take an example for the Diffie-Hellman, curve25519 Diffie-Hellman. So if you remember, Diffie-Hellman is basically g to the xy mod p, right? Where x and y are going to be between 0 and some prime. G is usually fixed. For curve25519, g is the number 9. And the prime is usually large. For curve25519, it's some sort of 2 to the 255 minus 19 or something like that. Okay? Doesn't matter. So how are we going to do these multiplications over large numbers? So we need a Bignum library, right? But Bignum libraries, what do we need them for? We need them for modular arithmetic. In particular, often we are going to be doing things like a to the b mod n, and so you're going to multiply a b times, well, naively, otherwise there are better ways of doing this, and each of these multiplications is a Bignum multiplication. So if you remember your textbook multiplication from your school, this is sort of what we do. When we're trying to multiply binary numbers, and if you try to do decimals, it's the same. We basically multiply digit by digit, we do the carry over, we compute the sums of everything, and that's our multiplication. That's textbook multiplication algorithm for us, right? And if you do Bignum multiplication over large numbers, it's pretty much the same. It just has larger sequence of bits on each line. So that's what happens if you're on a 64-bit computer. What you do is you take your 256-bit number, you break it into 4 or 5 or whatever until you have something which fits into 64 bits, and then you do almost exactly the textbook multiplication, right? You just multiply, carry over the bits, add everything, and once you have added everything, you want to do mod p, so you reduce the whole thing back to something that fits between 0 and p. Okay? So it's multiplication, addition, carry, reduce. That's sort of what happens in modular arithmetic for Bignums. So there are two questions to ask. What can go wrong, of course, that's what we will ask, but what people usually ask is how expensive is it? Because traditionally, Bignum arithmetic, whether it's for RSA or Diffie-Hellman, has been considered to be the most expensive part of a crypto protocol. Okay? So this is why people did not want to do Diffie-Hellman for a long time, because they thought that RSA was much cheaper. Now this is why people want to do elliptic curves, because they are considered way cheaper than mod p Diffie-Hellman. So and all of the expense of those things is in these Bignum computations. So how expensive is it? So if you have n 64-bit limbs when you're doing a multiplication, it roughly requires n square 64 times 64 multiplications. So it's kind of, it depends on how big your number is. For RSA, you might have like 16 or 32 limbs, so it's 32 square multiplications. For 256 bits, this is about 16 multiplications. What's basically the other kind of thing of the cost is that the intermediate arrays that you're using are kind of long. They get almost like double the size of the initial ones. You have many intermediate arrays, and you have to do many carry steps in order to make sure that you kind of keep carrying over, because all your additions could overflow and so on. And that's where a lot of the cost of these come from, the raw multiplication and from the carry steps. And what can go wrong? Well, since you have lots of arrays, which are these Bignums are no longer just numbers, they're arrays, right? and you're going to have to allocate these arrays, deallocate these arrays, manipulate them, and so on, you could have all kinds of errors that are happening. So when you're multiplying two numbers, suppose the result does not fit within 64 bits, you have an integer overflow, right? And an integer overflow in certain languages is undefined behavior. If you're using unsigned integer arithmetic, sometimes you use signed integer arithmetic. If you signed integer arithmetic, even in C, it's undefined behavior. But if you're using unsigned arithmetic, it's well-defined behavior. You just roll over to modulo 2 to the 64. But in fact, it might give you a completely bizarre result. So you have to be very careful that you're not triggering integer overflows. You can, of course, have buffer overflows because you're manipulating all these arrays and you might make a mistake somewhere and go outside the buffer zone, and now you're in heartbleed territory because this is all secrets that you're going to be doing multiplications over. Everything is a secret, so you don't know what you're going to be leaking if you go outside the buffer zones. You might miss some carry steps, and this is actually a very common bug that people do because they're trying to really avoid too many carries because carries are expensive, but if you miss some carry steps, you get the wrong answer, okay? And if you have the wrong answer, it might end up being an attack. Although going from the wrong answer in a Bignum multiplication all the way to an attack usually requires a lot of effort. And finally, there could be side channel attacks here because they might be leaking secrets. So what kind of side channels? Let's look at this example again. We are trying to multiply 1101 with 1010, and we have these 4 steps and so on. And we might look at it and we might say, look, you know what? This step over here, which is all 0, because I know if I know the bit there is 0, I know that this one is going to be all zeros and this one is going to be all zeros. I don't have to bother adding them and manipulating carries and all of that stuff. I can make this much more efficient by just eliminating those 2 steps and adding the whole thing. Now if you do this, of course it's much faster. You have fewer additions and carries, but you're leaking the fact that you had 2 zeros in your second argument, which might be a key. And now you're leaking more and more information. Okay? So an attacker who observes the runtime of this can actually guess what the second input was at least. So this is a classic, it's a trivial example, but this is kind of exactly the kind of side channels that appear in Bignum arithmetic. What makes it a little bit more complicated is that really you don't want to do this kind of Bignum arithmetic in a textbook fashion because it's too expensive, right? Because you have to do way too many computations. So for almost all the elliptic curves out there, for all the Bignum groups out there, people have many prime-specific optimizations that they implement. So what they want to do is to trade off the cost of multiplication versus the carry steps. So instead of dividing 256 bits into 4 limbs, you can, of 64 bits each, you can divide it into 5 limbs of about 51 bits each. And this allows you to multiply two of these limbs and then add them many, many, many times without doing any carries because you have enough room left in your limbs that you can actually use that room to collect some carry bits without having to actually propagate them. And this ends up being quite efficient. Furthermore, you might be able to use the fact that your prime has a particular structure to do your modulo p operation in a very efficient way. And this is again something that elliptic curves use a lot. And finally, you might want to do things in a parallel vectorized architecture to get even more speed. And all of these things change the Bignum multiplication from textbook to something fairly complicated, which increase the chances of bugs. Right? So for example, if you just look at the curve 25519 curve, in 2013, the fastest known implementation of that curve actually had a bug, which is a carry propagation bug. A similar bug came up in a more modern implementation, which is tweet salt, in another implementation, and so on. So these kinds of arithmetic bugs are actually very common. Okay, they're not nearly as common as memory bugs, I must say. Memory bugs are like the most common ones out there. Side channel bugs are quite common too, but this kind of arithmetic bug is actually quite common as well. So how about we verify that our code, our crypto code, is correct? Can we do that? And how do we do that? And we're going to use a language called F* to write a verified crypto library. And crypto is just an example. I'm just going to use it as an example to show how you can verify code. And of course, you can extend it up to whatever crypto construction or protocol that you want to use to verify. In particular, what we have done is verified these algorithms over there. And what we do is we write it in this language called F*, we verify it, and then we compile it down to C. Okay? And the library we have there is something that is enough to implement a full cipher suite of TLS 1.3 and also to implement the SALT API that's by Dan Bernstein. So we still have 5 minutes, I guess, something before we have to go? Okay. So let me kind of explain how the verification workflow works for HACL Star. So what we start from is there is some crypto standard which is published by the IETF as an RFC or by the NIST. And on the other end of the spectrum, there is somebody who's written optimized code for this in C or assembly or whatever, right? And our goal is to basically make sure that there is a link between these two, right? This distance between those two is going to get reduced. So the first thing that we do is you can take the NIST spec or the RFC, and you can transcribe that spec, hopefully in a very elegant manner, to what is called a pure spec in F star. This is the language that I'm going to show you what it looks like. And this spec is allowed to use certain features of the language. It can use arbitrary precision integers called int. It can use machine integers like 32-bit integers, 64-bit integers, whatever. It can also use arbitrary length sequences and so on. So it's like a specification where you can use things which may not be easy to implement efficiently. You can use whatever high-level concepts. Then you take the optimized code and you port it over to a subset of F star called low star, which is a subset of F star that looks just like C, so to speak. Okay? So you're going to port over your code to low star, and that low star code cannot use arbitrary precision integers, cannot use these beautiful any length sequences. Instead, it's forced to live in a world where it only has access to machine integers and to very limited form of arrays, which is like arrays over integers that you can use in C. And now that you have these two implementations, one which is a spec, which is an F star, and the code which is also an F star, but in a subset of F star called low star, we can now do the verification. So we can take the spec and the implementation, link them together, and try to prove that the code matches the specification. This is called functional correctness. That the code that never accesses non-live memory contents and never accesses things outside bounds, which is called memory safety. And to prove that the code is secret independent, which is a form of side channel resistance, a limited form of side channel resistance. And all of this is verified using a type checker called F star, the F star type checker. And if F star succeeds, you're guaranteed that you don't have any of those bugs in your code. And if F star fails, then you potentially have a memory safety bug or a side channel or a functional correctness bug. Okay? Usually you have them and you can tell what the bug is. Sometimes it might be hard to tell what the bug was. If you succeed, then you can run your compiler, and the compiler is going to check that your program is actually in a form that can be compiled to C, and it's going to spit out C code for you, which you can run, compile with GCC, Clang, CompCert, whichever your favorite compiler is. So what's the source language? The source language is called F star, and I'm going to show you this slide, and then we're going to pause, and we're going to do more F star stuff after we get back. And I'm going to show you some code samples in F star and how you can use it to verify not just crypto, but protocols and other kinds of things. So F star is a language that you can get at that, go to that URL. It's all developed on GitHub. It's a functional programming language. If anybody here has programmed in OCaml or Scheme or these kinds of languages, F sharp, it's a language of that kind. And it has a customizable verification system. So it's both a programming language and a verification system. And a verification system, I mean something like Coq or Isabelle or this kind of thing. And you can do, and one of the key features of F star is that most of the boring proofs, or hopefully most of the boring proofs, are automatically discharged by a SMT solver. And we use a Z3 SMT solver for it. So which means that a lot of the stupid things like showing that the loop invariant loop stays within the bounds, or you're not writing outside the bounds of the buffer, or that the program terminates even, can be automatically proved just by calling Z3. And finally, once you've proved your code, it has compilers which go to OCaml, which to F sharp, to C, and now there's one that goes to JavaScript and WebAssembly as well. So you can actually prove your code in this nice language, and then you can spit out whatever target language that you want. So that's the language you're going to look next. But I think we should stop now because we need to empty this room out. Yeah?